This just in, Mr. Shopke assigns a take-home math test.
What?
You heard that right, a take-home test.
We have two boys out of Atlanta, Georgia who claim to have answered all the questions on the test. They sent us in a video with an explanation of their answers.
Let's go ahead and watch it now.
Hi, my name is Mason Cohen.
And my name is Nathan Dunnigan. And we're in Mr. Shopke's math class, and we're completing his take-home vectors test. Question 1 gives us an equation of a plane, an equation of a line, and the angle between the line and plane. The question asks us to solve for a missing variable in the equation of the line, seen right here as p. We will be using the variable u for the direction vector of the line, which is 1, -2, and p, and the variable n for the direction vector of the plane, which is 2, 1, and 2. Because we are dealing with an angle between a line and plane, we set the dot product of u and n, seen right here, equal to the magnitude of u times the magnitude of n times sine theta. The steps to following the dot product are as follows. You will multiply the numbers across and add each product to each other. So we do 1 times 2, which is equal to 2, -2 times 1, which is equal to -2, and p times 2, which is equal to 2p. After adding up 2 plus -2 plus 2p, we get 2p. 2p is therefore the dot product of u and n. Next, we must find the magnitude of u and n. To find the magnitude, you square all the numbers, add them up, and then take the square root of the sum. So, for the magnitude of u, we added 1 squared, which is 1, -2 squared, which is 4, and p squared. The sum of those is 5 plus p squared. Then we must take the square root of those numbers. So we have the square root of 5 plus p squared equal to the magnitude of u. Next, we must find the magnitude of n. 2 squared is equal to 4, 1 squared is equal to 1, and 2 squared again is equal to 4. The sum of those numbers is equal to 9. Taking the square root of 9 will give you 3. Then we simply plug in 30 for theta as it is given in our equation right here. And luckily for us, sine of 30 is on the unit circle, so of course we know that that value is equal to 1/2. So after finding the dot product is equal to 2p, the magnitude of u, which is equal to the square root of 5 plus p squared, the magnitude of n, which is equal to 3, and sine of 30, which is equal to 1/2, we were able to use simple algebra, seen in these steps right here, to isolate p squared and then solve for p. So we were able to get p squared equal to 45/7. Then we took the square root of each side, and we were able to set p equal to positive or negative square root of 45/7, which is our answer.
In question 2, we were tasked with finding the minimum distance between two moving ships, given their position vectors after time t hours after midday. First, to visualize the problem, we drew this diagram. Given that we have the position vectors of each ship, they can be represented as these 2 points on 2 lines, or 2 vectors. Then, to find the distance between these 2 points, we subtracted ship A's position from ship B's. This subtraction yielded the vector 3 minus 5t for the x-coordinate and -6 plus 4t for the y-coordinate. We then plugged those values in for the distance formula, as shown here, and we're left with the square root of the quadratic 41t squared minus 78t plus 45. In order to finish solving the problem, we plugged this equation into our calculator and used the trace function of the calculator to find the minimum. This gave us an answer that the minimum occurred at 0.951, or x is equal to 0.591, and the y-coordinate is 2.81. So therefore, the ships are at a minimum distance away from each other at 2.81 kilometers.
In question 3, we were given points A and B and point C's position vector. And then we are given that O was equal to the origin, and we're asked to find the dot product of OA and OC in terms of K. First, we must find OA. To find OA, you subtract O from A. So we took A, which is -2, 4, and -4, and subtracted O, which is 0, 0, 0, from it to get OA equal to -2, 4, -4. Next, we had to find OC. To find OC, we did the same method as in OA. We found C, which is negative 1, K, 0, and subtracted O from C, which is 0, 0, 0, to find that the vector OC is equal to negative 1, K, 0. Similar to question 1, we did the same method in finding the dot product. We did negative 2 times negative 1, which is equal to 2, 4 times K, which is equal to 4K, and negative 4 times 0, which is equal to 0. Then we added up the products to get 2 plus 4K is equal to the dot product of OA times OC. Next, in 3b, we are tasked with finding the dot product of OB and OC. To find OB, we use the same method as in 3a. We have B, which is equal to 6, 8, and 0, and subtract O from B, which is 0, 0, 0, to get OB vector is equal to 6, 8, 0. Next, we do the same thing with the dot product. We do 6 times negative 1 is equal to negative 6, 8 times K is equal to 8K, and 0 times 0 is equal to 0, to get the answer of 8K minus 6.
In question 3c, we were asked to show that k is equal to 7, given that angle AOC is equal to angle BOC. In order to do this, we needed to utilize the formula u dot product of n is equal to magnitude of u times the magnitude of n, which is times cosine of theta. So if you look over here, I ascribed what each vector would mean. So O to A would be u, v would be O to C, w would be O to B, and then v would be O to C once again. So in our problem, we set 4k plus 2, because that is the dot product of OA or OC, or the dot product of u dot v, equal to the magnitude of u times the magnitude of v times cosine of theta. We then solved for cosine of theta by subtracting 6 times the square root of 1 plus k squared on both sides. So cosine of theta for the dot product of OA and vector OC is 4k plus 2 over 6 square root of 1 plus k squared. We did the same steps for 3b for 8k minus 6, which we found from 3b. The dot product of OB and vector OC is 8k minus 6. The magnitude of OB is 10, and the magnitude of OC is 1 plus k squared. Multiplied by the cosine of theta, we know that we can once again divide both sides by what cosine of theta is with to find two equations where cosine and theta are both equal to some number with k. Then we set these two equations equal to each other, given we know that angle AOC and angle BOC are the same, and we solved for k as shown by the steps here involving cross multiplication, division, subtraction, and addition to show that k is equal to 7. Then, for 3D, we needed to find the area of triangle AOC. So, in this problem, the area of the triangle is, the equation that we use to find the area of the triangle is area equals 1/2 times the cross product of u dot v. So, like I said, we know that u is the vector OA and v is the vector OC. In order to do cross product, we have to complete something called a matrices. In order to do this, you write ijk across and horizontally, and then beneath you write the values for ijk for your two vectors. So, because vector OA is -2, 4, -4, then we wrote -2 for I, 4 for j, and -4 for k. So this second horizontal row is OA. Then we repeated the same steps for OC, plugging in 7 for k, given that we just showed that k is equal to 7 in 3c, and we wrote -1, 7, 0. To complete the matrices, you write out I and then a small box minus j, because the j coordinate is always subtracted, and then plus k, because the k coordinate is always added. The four integers that go inside this box are the ones not associated with the given variable. So for I, we use the 4 integers that are not a part of I. So we did not use -2 and not -1. And then you write them as they appear in your larger box. So 4, -4, 7, 0. The same applies for j. Because we're working with j, we do not look at our j column when we are writing the smaller box. So we wrote -2, -4, -1, 0, keeping the same positions of the numbers. And then we did the same for k. In order to solve from there, you must multiply this number by this number and subtract that by this number multiplied by this number. So the product of 4 times 0 is 0, and the product of 7 times negative 4 is negative 28. So 0 minus negative 28 gives you positive 28, which we have here, 28, and then multiplied that by the variable is I. The same is repeated for j. Negative 2 times 0 is 0. Negative 1 times 4 is positive 4. 0 minus 4 is negative 4. However, because we are already subtracting from j, we are doing minus negative 4j, which is really positive 4j. And then, once again, the same steps repeated for k to give you an answer of negative 10k. Finally, in order to calculate the area, we know to take the square root of the 4 coefficients of I, j, k, given that that would be the cross product of the formula we have here. So that gives us the square root of 900, which is equal to 30. And finally, following the formula, we multiplied by 1/2, which gave us 15. So the area of triangle AOC is 15 units squared.
For question 4, we were given 3 equations of planes, and we were asked to find a set of values of A and B such that the 3 planes have no point of intersection. To start, we multiplied the second equation by 2, and we subtracted that from the first equation to cancel out the x variable, and we got the new equation of negative 7y plus 3z equals negative 3. Then we had to use 2 different equations to cancel out the x variable again. So we multiplied the second equation by negative 3 and added it to the third equation. This canceled out the x variable, and we got negative 14y plus 3 plus az equals b minus 12. Then, with these 2 new equations, we were able to see that they were simply multiples of each other. If we were to multiply this first equation by 2, we would get negative 14 plus 3 plus az equals b minus 12. So, when equations are multiples, they intersect and they have infinite solutions. And we were asked to show where there are no points of intersection. So we want to prove that they are not multiples. And to make this equation a multiple, we would have to have a equal to 3, because then this would be equal to 6z, which is 3 times 2 equal to 6z. And b would be equal to 6, because 6 minus 12 is negative 6, which is a multiple of negative 3. So we came to the conclusion that if a is equal to 3, then b is equal to any number besides 6. And if b is equal to 6, then a is equal to any number besides 3.
In question 5, we were given the equation for a line 1, and a point P, which lies on the line. However, one coordinate of the point, the z coordinate, is missing, which they have as C. So, in order to find C, we must first solve out the equation of the line by taking negative 3 and adding it to 6 times s, taking 9 and adding it to s times 0, and taking 10 and adding it to 2 times s. So we see that here. We can then set those equal to the point on the line, given that we know that this first row is the x-coordinate, the second row is the y-coordinate, and the third row is the z-coordinate. So negative 3 plus 6s is equal to 15, 9 is equal to 9, and 10 plus 2s is equal to c. Then we found 6s is equal to 18 by adding 3 to both sides, and found that s is equal to 3. We took that s is equal to 3 and plugged it into our other equation with s, and found that c is equal to 16, because 10 plus 2 times 3 is 16. Then, for 5b, we were told that there is a second line, L2, which is parallel to L1 and passes through the point 1, 2, 3. A vector equation for L2 is what we were required to find. Well, given that we know any equation any lines that are parallel to each other have the same direction vector, we were able to keep the direction vector 6, 0, 2, and s. Then, to find an equation of a line with this direction vector that passes through the point 1, 2, 3, all we need to do is copy down that same point and add it to the direction vector, which would give us the final equation of the line for L2.
we would also like to point out that you can use any multiple of the direction vector and it will still be parallel. Question 6a gave us a triangle with 3 coordinates and asked us to find, in terms of b, a Cartesian equation of the plane containing this triangle. First, we had to find 2 vectors on this plane by using the points given to us in the triangle. To do this, we used points O and points A to find vector OA. I subtracted point O from point A to get the vector OA is equal to 0, 1, 2. Then I did the same thing for vector OB to get 2b, 0, and b minus 1. Next, we did the cross product of these 2 vectors, which we explained earlier how to do step by step. So, I got b minus 1i plus 4bj minus 2bk to get n is equal to b minus 1, 4b, negative 2b. N is the normal of the vector. So we use this normal in the equation r times n equals a times n. R is x, y, and z always, and a is any position vector given. So we use this equation to find the Cartesian equation. So we do x, y, z times b minus 1, 4b, negative 2b. And this is simply just the dot product. So we have b minus 1x plus 4by minus 2bz. Then I chose to use the position vector 0, 1, 2 and multiply it by the normal to get 4b plus negative 4b, which is equal to 0. So our Cartesian equation was b minus 1x plus 4by minus 2bz is equal to 0. Then my partner decided to do 2 different vectors to show that our equations still work. He did vectors AO and AB. So he subtracted A from O to get vector AO is equal to 0, negative 1, negative 2, and AB is equal to 2b, negative 1b minus 3. He then did the same process with the cross product to get the opposite normal. So he had negative b plus 1, negative 4b, positive 2b. So our normals were simply just opposites of each other. However, you can see that despite the normals being opposites, we still got a Cartesian equation of negative b minus 1x minus 4by plus 2bz equals 0. Both these equations work. In 6b, we are told that M is the midpoint of the line segment OB, and we know that the midpoint equation is x1 plus x2 divided by 2, and so on, y1 plus y2 divided by 2. And so for M, we look at O, which is 0, right up here, 0, and we know that for B, x is 2b, so we do 0 plus 2b divided by 2, and so on, 0 plus 0 divided by 2, and 0 plus b minus 1 divided by 2. And we get M is b, 0, and b minus 1 over 2. And that gives us our position vector. Then we are told that line L passes through M and is perpendicular to plane 2. And we know plane 2, which equation is right here. And we know that the normal vector is a vector which is perpendicular to the surface at a given point. And since we are told that line L passes through point M and is perpendicular to the plane 2, we use that normal vector that we found up here as our direction vector to find the line L.
In order to solve 6c, we needed to use the equation that we found in 6b. Now remember that because Nathan and I solved 6a differently, our direction vectors for the equation for the line were opposite, with opposite signs for each variable. So for the purpose of solving 6c, we used the line equation that Nathan found with the direction vector b minus 1, 4b, and negative 2b. We thought about this problem logically and realized that if this line were to intersect the y-axis, x must be equal to 0 and z must be equal to 0, or x is equal to z. Then we used the equation of the line to solve out for the x and z coordinate. So b plus lambda times b minus 1 equals 0 for x, and b minus 1 divided by 2 plus lambda times negative 2b equals 0 for z. Then we solved for lambda in both of these situations and set those equal to each other. So over here, b minus 1 over 4b, and then negative b over b minus 1 equal to each other. I cross multiplied and found that 4b times negative b is negative 4b squared is equal to b minus 1 squared. Now, if b were to be negative on the left-hand side, we would have a negative times a negative squared, which is a positive. So a negative times a positive is negative. So the left-hand side of the equation is negative. However, on the right-hand side, if b were negative, we would have a negative squared, because if b were negative 2, we would have negative 3 squared. If b were negative 1/2, we'd have negative 1 1/2 squared, etc. So this side will always be positive because a negative squared is always positive, because a negative times a negative is positive. Therefore, if we have a negative on one side and a positive on the other, the equations can never be equal to each other, meaning that there is no intersection when b is negative. For the last question of the test, we're given 3 vectors, OA, OB, and OC, and for 7a, we're asked to find the vector equation of the line for BC. Well, given that O is the origin, we know that these vectors are actually, the coefficients of these vectors are really just the points for A, B, and C, given that O is the origin. So, to find BC, we would subtract what we have for C and by B. So C is 1, 3, 3, and B is 2, negative 1, 2, giving us negative 1, 4, 1. When we subtract these two vectors, we're going to get the direction vector for that line, and then all we need to do is have a point on that line plus that direction vector to have the vector equation of the line. So we know a point on the line would be either point B or point C, so we could have used 1, 3, 3 here, or we could have used what we did, which is 2, negative 1, 2, and then we just added it to the direction vector that we found with our variable lambda. So BC is 2, negative 1, 2 plus lambda, negative 1, 4, 1. Then for 6b, we sought to determine whether OA and BC intersected. Now we already find the vector equation of the line for BC, so we needed to find the vector equation of the line for OA. The steps are the same because we have the a point on the line, the origin, plus a direction vector, which we know is 2, 1, negative 2 from up here. We need to have two different variables here so that we can, at the end, solve to see if they intersect, given that these are two different vector equations. So we solved out here from OA to find that 2s would be equal to 2 minus lambda, because these are both the x coordinates. So this is x here, this is y, and this is z. Y, we have 0 plus s, which is just s, and then negative 1 plus 4 lambda, so 4 lambda minus 1. And then for z, same steps, 0 plus negative 2s, 2 plus lambda. Since our y coordinate yielded something for s is equal to 4 lambda minus 1, we can use this and plug it into our equations for x and z. So 2 times 4 lambda minus 1 is equal to 2 minus lambda, and lambda is equal to 4/9. And then here, negative 2 times 4 lambda minus 1 is equal to 2 plus lambda, and lambda is equal to 0. Because we have two different values for lambda when y is equal to s, which is equal to 4 lambda minus 1, then we know that these lines do not intersect.
For 7c, we are asked to find the Cartesian equation of plane 1, which passes through C and is perpendicular to OA. So for n, I used the normal from OA, which is 2, 1, negative 2. So I multiplied x, y, z by 2, 1, negative 2 to get 2x plus y minus 2z, and then I multiplied 1, 3, 3 times 2, 1, negative 2. And I used 1, 3, 3 for A because we are told that it passes through C. And for C, point C is 1, 3, 3 because we found that out earlier in the equation. So our Cartesian equation is satisfied when we do the dot product of 1, 3, 3 times 2, 1, negative 2, which gives us the answer of negative 1. So our Cartesian equation is 2x plus y minus 2z equals negative 1. Next, in 7d, we are told to show that the line BC lies in plane 1. BC, we found earlier, is 2, negative 1, 2 plus lambda 1, negative 1, 4, 1. And so we broke down x, which is 2 minus lambda, y, negative 1 plus 4 lambda, and z, 2 plus lambda. Then lambda, sorry. Then we plug in x, y, and z into the Cartesian equation that we found above. So after plugging it in and doing simple algebra, which I won't go into depth, we find that -1 equals -1, proving that line BC does indeed lie in plane 1.
Okay, so for question 7e, we're told that the plane 2 contains points OAB and plane 3 contains points OAC. But for 7e, we're only asked to look at plane 2 because we need to verify that 2j plus k is perpendicular to plane 2. In order to do this, we need to find the cross product because the cross product tells us the normal line of the plane. So because OA and OB are contained within the plane, doing the cross product will yield the Cartesian equation for the plane, which we found to be 8j plus 4k, as seen here. However, because we are told that 2j plus k is the normal line to plane 2, we know that you can multiply that by 4 and get 8j plus 4k. In other words, the Cartesian equation, or the normal line that we found, is a multiple of the normal line given by the problem. And as written by the statement, if vectors are multiples of each other, then they both must be normal to the plane and therefore must both be perpendicular to plane 2. So we have verified that 2j plus k is perpendicular to plane 2 because it is a multiple of 8j plus 4k, which we found through the cross product. The steps are the same for 7f, given that we're asked to find a vector perpendicular to plane 3. We know that we must take the cross product of vectors OA and OC because those are the points contained within plane 3. Doing so yields the Cartesian equation of a plane, 9i minus 8j plus 5k. And because the coefficients of I, j, and k make up the Cartesian equation for a plane, the perpendicular vector is therefore 9, -8, and 5. Finally, for 7g, we're asked to find the acute angle between planes 2 and 3. Now, the equation that we must use in order to find an angle between two planes is the cross product of two normal lines, which is equal to the magnitude of normal line 1, magnitude of normal line 2, times the cosine theta of the angle in between. So the normal line is the line that is perpendicular to the two planes. And so here we know for what we found in 7e, the normal line is -8j minus 4k, and the normal line for plane 3 found in 7f is 9i minus 8j plus 5k. The dot product between the two is therefore 0 times 9 plus -8 times -8 plus -4 times 5, which is all added together and equal to 44. And then that is equal to 0 squared plus -8 squared plus -4 squared, and then the square root of that sum, so the square root of 80. And then the same for normal line 2, 9 squared plus -8 squared plus 5 squared, and the square root of that sum, which is square root of 170. So we get 44 is equal to 80 times 70, and then keep it under the square root, 13,600 cosine theta. We then divide both sides by the square root of 13,600 and take inverse cosine of both sides to find that the acute angle for the angle in between the two normal lines, or the two planes, is 67.83 degrees. Wow, that was really great.
Honestly, it's great to see two young men working hard on math.
Fingers crossed that those boys receive an A.
Really great work.
In other news, the Alabama Crimson Tide rolled over the previously undefeated Georgia Bulldogs in the SEC Championship yesterday. Nathan, can't say I'm surprised. What do you have to say about yesterday's loss?
Well, go Dogs.